morning.
Good morning.
Before we start going through the screen stuff, I'm just going to talk a little bit about the nature of our four-dimensional space-time. Our four-dimensional space-time is rather a weird space. It's four-dimensional, and so you should expect that it would have a four-dimensional rotation. It doesn't. It has two-dimensional rotations. That's not natural. A four-dimensional space should have a four-dimensional rotation. Quaternion space is four-dimensional. It has a four-dimensional rotation. That's a rotation matrix that's 4 by 4 with 4 different trigonometric functions in it. The 4 trigonometric functions of the quaternions that were discovered by William Hamilton in 1843. Why have we got two-dimensional spaces? It gets even weirder. We've got two types of two-dimensional rotation in our four-dimensional space. We have the normal two-dimensional rotation in the Euclidean plane. We've got 3 of those in 3 different planes. And we've got rotation in two-dimensional space-time, which is change of velocity. Change of velocity in that direction, in that direction. So we have 2 types of two-dimensional rotation in our four-dimensional space-time. It's rather weird. The other thing that you will come across often in mathematics, and it's been around for over 2,000 years, is the idea that a four-dimensional space is 4 one-dimensional spaces stuck together with chewing gum, or by some other means. The 4 one-dimensional spaces do not have angles in them. They don't have any concept of being orthogonal to each other. And so if you're going to construct a space out of one-dimensional spaces, you're going to need some chewing gum, you're going to need to get some angles from somewhere, and some concept of orthogonality. What we in fact do is we pinch the angles out of the complex plane, and we pinch them out of the hyperbolic complex numbers. In short, the generally understood structure of four-dimensional space-time is pure nonsense. The same is true of any space that's formed of n copies of the real numbers. It just doesn't hold together on its own. You need more structure to get the space. Having said that, I'm going to point out 1 or 2 other little things. In our four-dimensional space-time, because we have rotation in 2 dimensions, we've got a spare spatial dimension, and so that can become the axis of the rotation. If you look at quaternion space, it's a 4-dimensional rotation in a 4-dimensional space. There's no spatial axis spare to be an axis. So rotation in quaternion space is not rotation about an axis. The same about the complex plane. You can rotate in 2 dimensions in the complex plane, but there's no 3rd dimension to be the axis. We tend to look at it and think, there's an axis sticking out from the origin. But there isn't, because the complex numbers are 2-dimensional. So you do not get rotation about an axis in a natural space, as I might say. Right, we'll now talk about the nature of algebraic structure. What I'm going to assert in this talk is that empty space is the same thing as you got that?
Does the camera have to point at this?
I think they're getting all this.
They're getting it all anyway. Okay.
Yeah. What I'm going to assert is that the proper form of empty space is an algebraic structure. The complex plane is a proper type of space. It's also a type of algebra. It's the algebra of the complex numbers, a type of number. Quaternion space is a proper space. It's a geometric structure. It has angles in it. It has trigonometric functions in it. The trigonometric functions are what we call the polar form. Right. Normally, your algebraic field would be defined by 14 field axioms. These 14 field axioms, one of these is the existence of additive inverse, minus numbers on the real axis, and of the additive identity as a naught on the real axis. Two-dimensional space-time does not have a naught on the real axis. If you look here, that's where the naught is. There are the asymptotes. Two-dimensional space-time starts here, it's within here. This is the two-dimensional space-time plane. It's inside that blue hyperbola. That is not an algebraic field by standard algebraic field axioms. Where do the axioms come from? Can we scroll this down?
I think you use the arrow keys, so they're not working.
They're not working.
The page down.
Mouse. Oh,
Press the button in the middle of the mouse, the thing in the middle of the mouse. That's the only thing I've got that works.
oh,
Yeah.
it's not giving us. Leave down, please. Yeah, we can have. Right. If we ask where do these 14 axioms come from, the truth of the matter is they're copied out of the complex numbers. People like David Hilbert sat down, they looked at the complex numbers, wrote down 14 properties of the complex numbers, and said, they're the 14 axioms of an algebraic field. They ignored some of the properties of the complex numbers, and they picked on others. We can equally decide to look at the complex numbers, and we can pick out 14 different properties of the complex numbers and declare that to be an algebraic field. And I'm going to do that. I'm going to say, if there is a polar form, if there is trigonometric functions within the algebra, then it's an algebraic field. So I'm identifying an algebraic field with a space that's got trigonometric functions in it. It's got geometric structure. It's got angles, it's got distance with it. So we're taking them slightly different. When we do that, we find that two-dimensional space-time, which really exists, is an algebraic field. That's the rotation matrix of two-dimensional space-time. Where does it come from? Well, it comes from the exponential series. We start with the exponential series. Within the exponential series, we find the exponential series inside the real numbers. It's just a set of real numbers. We split it in half, and we get the cosh function and the sine function. When we've got the cosh function and the sine function, we've got two-dimensional space-time. So straight after the exponential series, two-dimensional space-time is dropped out. And it dropped out as an algebraic field because it's got polar form and it satisfies all the other axioms that are needed for an algebraic structure, apart from the ones on the additive inverse and additive identity on the real axis. What we actually did when we picked out every second term of the exponential series is we applied the finite group C2 to permute the terms of the series. There's a group, a little bit higher. There's a group C2, it's two permutations. It's represented as permutation matrices. We just multiplied each one by a real number. We got an algebraic matrix form, we took the exponential, we've got the rotation matrix of two-dimensional space-time that physicists often call the Lorentz boost. This is change of velocity. What we do with C2, we can do with any other finite group. We're going to do this one with C4. C4 is an order 4 group, but we're going to use the signed permutation representation. Effectively two representations for finite groups. There's a signed permutation representation, which has a 1 or a -1 in every row and every column, and not elsewhere. And there's a permutation matrix one that just has 1s in every row and every column. That's what you might call the regular representation. This is the signed permutation representation. We do the same again. We multiply the permutations by a real number, add them together, and lo and behold, we've got the complex numbers. You might be familiar with the idea that the complex numbers are associated with a polynomial, x squared plus 1 equals 0, that can't be split into linear factors without using the square root of -1. That's true, but it's not the essence of the complex numbers are about. The essence is they come out of the group C4. They are a C4 permutation of the exponential series. Right. So, what we do with those groups and do any other group. Remind me what I'm saying is that the mathematical apparatus of two-dimensional Euclidean space is the complex numbers. I'm doing away with any concept of R2, just sticking real numbers together with a bit of chewing gum. We're saying that our two-dimensional space, this is a rotation in the complex plane, as is that, and as is that. And I've already gone through only our four-dimensional space-time as rotation about an axis. Rotation in the complex plane is not about an axis. This is of importance when we think about electrons, which we will do in due course. Come to a proposition. All algebraic structures, that's all types of complex numbers, are within the exponential series. And you form them by applying a finite group to permute the terms of the exponential series, to pick out the terms of the exponential series. It turns out that the polar form of the algebra is the algebra, not the Cartesian form. In two-dimensional space-time, if you try to use the Cartesian form of the algebra, it doesn't work. We have zero divisors. There's zero divisors. There'd be the two elements of a two-dimensional space-time written in a Cartesian form, and it looks like we've got two elements that are non-zero that multiply together to make zero. You can artificially restrict the Cartesian form to make it work, but you don't need to, because the cosh function is always greater than the shine function, and so you get no zero divisors within an algebraic field in polar form. If you're not careful and you use the Cartesian form, you might come across zero divisors. So really, you should do your algebra in polar form. It's easy to do it in Cartesian form as long as you're aware of the fact that you've got to watch out for these zero divisors. What you can do, you can look at these imaginary roots, look at the complex numbers that have imaginary roots. Imaginary roots of +1 and -1. The square roots with plus 1 are the ones that give you the problems with the zero divisors. Now, the finite group is a set of permutations, and what you do, you get any permutation, you combine it with itself once, combine it with itself again and again and again, and eventually you get back to the identity. So in a way, every permutation is a square root or a cube root or a fourth or a fifth root of the identity. So it's like plus a fourth root or a third root of +1 or square root of +1. There are some elements which are the involutions of the identity in the group, which correspond to a -1. So you can get, within C4, you get the permutation, you combine it with itself, you get the involution of the identity, you combine it with that's like equivalent to -1, you combine it with itself again, and you get back to the identity. So it's like a fourth root of +1 or a square root of -1. We'll use a three-dimensional example. This is the group C3. What we've done, we've taken the three permutations. This is the permutation representation. We've multiplied it by a real number. We've taken the exponential, and out come the trigonometric functions of three-dimensional space. There are 4 three-dimensional spaces, because there are also some representations, three-dimensional representations of C6. Well, this is the representation of C3. These are three-dimensional trigonometric functions. We've never seen three-dimensional space in our life, and we never will. But it is a complete bona fide algebra. We can, if we're careful about the zero divisors, we can write it as cube roots of +1, cube roots of -1. They're the 4 actual algebras that we have. It turns out that Clifford algebras are those underscored by those particular groups that have only C2 and C4 as subgroups. That's why you only get square roots of +1 and -1. Assertion. All types of space, that's all algebraic structures, and I'm talking algebraic fields here, are from within the exponential series. That's the whole of the types of number that there is. There is no other types of number. The exponential series has got the lot. But every one of these types of numbers, like the complex plane, is an empty space. So we've got all types of space. Turns out that these are gauge potentials. So every possible type of space, we've got every possible type of rotation. Each rotation holds invariant a particular distance, a distance from the origin. That distance is measured in a particular way. two-dimensional space-time, the distance is t squared minus z squared. For two-dimensional Euclidean space, it's x squared plus y squared. For three-dimensional space, it turns out that the distance cubed equals a cubed plus b cubed plus c cubed minus 3abc. So we've got all possible rotations, we've got types of rotation, we've got all possible distance functions that are held invariant by these rotations. Two of these rotations, the two-dimensional ones, appear within our four-dimensional space-time. Last year, I presented the case where we deduced the existence of four-dimensional space-time as a superposition of the spaces that come out of the order 8, the four-dimensional representation of the order 8 dihedral group. There are 6 such representations. 3 are left-handed, 3 are right-handed. The handedness is in the commutation relations. You take a superposition of either set of 3 and you get four-dimensional space-time. You get right-handed four-dimensional space-time, left-handed four-dimensional space-time. We are sitting in a superposition of 2 four-dimensional space-times, the left-handed one and the right-handed one, and each is a superposition of these 3 gauge spaces that come out of the order 8 dihedral group four-dimensional representation, and it's unique. There is no other finite group that has a superposition space that has geometric structure. They all have distance functions that have no room for a geometric structure. For example, the 3-dimensional spaces, if you add up all the distance functions, you get distance cubed equals a cubed. There is no rotation that holds invariant distance cubed equals a cubed. We've got distance squared equals x squared plus y squared, distance cubed equals a cubed plus b cubed plus c cubed minus 3abc, but we haven't got distance cubed equals a cubed. So you can't fit any geometric structure into the group superposition space with a single exception of the group D4, four-dimensional representation. That's why we live in a four-dimensional universe, and there are no other superposition spaces out there. Our four-dimensional universe is unique. It is not an algebraic space. It's the only non-algebraic space with geometric structure. It can have geometric structure because the superposition distance function, distance squared equals t squared minus x squared minus y squared minus z squared, you can fit 2-dimensional rotations into it by setting 2 of the variables to 0. Because you can fit 2-dimensional rotations into our 4-dimensional space-time, you can fit 2-dimensional curls. And so the forces that we see in the universe are the set of 2-dimensional curls. What we did last year is we differentiated the gauge spaces. When we differentiate non-commutative gauge space, we have to do a non-commutative differentiation. We get 2 differentials, dy times 1 over dx, 1 over dx times dy. That splits a 4-dimensional curl into 2 2-dimensional curls, and so the quaternion curls, you get 2 quaternion curls that are 2-dimensional. That gives us the electron field and the neutrino field. In fact, you get the left-handed electron from the left-handed quaternions, the right-handed electron from the right-handed quaternions, left and right-handed neutrinos, but the superposition gives you an unhanded electron and a left-handed neutrino. We get classical electromagnetism plus gravity and gravitomagnetic field out of the dihedral group D4. The gravitomagnetic fields cancelled, leaving behind gravitomagnetic field energy, which is dark matter, and the quark fields come out of the Clifford 8-dimensional Clifford algebras, whose superposition also reduces to 2-dimensional spaces. They're the only ones. We've got all the fields of the... So we've got unified field theory. Later on in this talk, we're going to go a little bit further than that. We're going to discover quantum phenomena. Right, I'm now going to talk about the nature of algebraic operations. Every trigonometric function corresponds to a permutation. We're going to just do a little bit of complex numbers by just using permutation. So what we're doing, we're multiplying these 2 numbers together, a plus ib and c plus id, and we're going to write them as permutations. And what we're actually doing when we take the matrix product, we're actually sequentially joining permutations together. So we're sequentially combining permutations together. And of course it all works. This tells us one thing. Multiplication is the sequential combination of permutations, which means if you're working in a field that does not have permutations, for example, Lie algebras, you cannot multiply things together. So to speak properly, Lie algebras are just a bag of nonsense. There's something invented by mathematicians and fudged to pretend that they exist, and they're doing it wrong. They should be using the non-commutative finite groups, which are proper permutations, rather than just making stuff up. There are other stuff out there, Kac-Moody algebras and stuff like that, which don't have multiplication in them. If they don't have multiplication, they're not a proper algebraic structure. That doesn't mean they're not useful, but it does mean they're not a proper algebraic structure. Adding things together to take the superposition, well, potentials do this all the time. You get electric field from an electron here, electric field from another electron here. The potential in the middle is just the sum of the two fields. This is what potential is, because they are linear. Everything here is linear. Now go on to Clifford algebras. Clifford had the idea of bivectors and trivectors. The concepts are, to my mind, complete nonsense. But what Clifford algebras actually are, they are algebras whose underlying groups are of the form C2 cross C2 cross C2 cross C2 cross C2 cross C2. They have C2 subgroups and C4 subgroups. The C2 subgroups give you square roots of +1. The C4 subgroups give you square roots of -1. This is the 32-dimensional one. In the Cartesian form, they have 0 divisors, but you don't use the Cartesian form, you use the polar form. You use the Cartesian form because it's easier, but be conscious of the fact that it should be the polar form. What the elements of a Clifford algebra actually are, they're not bivectors or trivectors, they're just permutations multiplied by a real variable. And you do your Clifford algebras as matrices. Here we have, this is a dihedral algebra. Right. So basically, what I'm saying is that a bona fide space, to be a bona fide space, you've got to have rotation, you've got to have angles, that means you've got to have trigonometric functions. The only things that have that are algebraic fields. They're underpinned by a group, and any finite group you want, you can take representations either as the regular representation or as signed permutation representations when they are available. They're not available to groups of odd order. And you'll get a space, you'll get a set of trigonometric functions in a rotation matrix. You've got your geometric structure. These act as gauge spaces. Our four-dimensional space-time is a superposition of a special set of these from the dihedral group, which differentiate the gauge spaces. We've got the unified field theory. Great, smashing. We've got every field, we've got unified field theory, but there's no mention whatsoever of the weird quantum phenomenon. Last year, we got all the unified fields. Yeah, great, smashing. But we didn't consider things like Schrödinger's cat and the weirdness of quantum mechanics. It was all classical. We got Maxwell's equation, we've got the equations of motion for the other stuff, quarks and things. I didn't show you them though last year. But now, when we come to look at the world, we get some weird phenomenon. Schrödinger's cat, it was summarised back in the 1920s by Schrödinger. Right, Schrödinger's cat. Schrödinger got a cat and he put it in a car boot with a poison glass vial of poison gas with a radioactive atom attached to it. And if radioatom decayed randomly, the cat would be killed, and if it didn't, it'd be alive. Then he shut boot at the car and he said, until I open that car and observe it, that car boot, and observe the cat, it is in a superposition of being both dead and alive. The concept of superposition there, it's actually in a superposition of being both dead and alive, or half dead, or a third dead, or whatever. And when he opens the boot of the car, it collapses from being in a superposition to being in an eigenstate, particularly you see that dead or it's alive. We see the same thing when we throw an electron at two slits. We throw an electron at a screen with two slits in it, and we say, which slit does it go through? And as long as we don't observe it, it goes through both slits. What is the trajectory of that electron? It's a superposition of going through both slits. We stick an observer by the side of the slit, it went through there, and it collapses. This is all the kind of weird stuff we get from quantum mechanics. Richard Feynman came along, he put a third slit in and a fourth slit, and eventually took the whole card away, and he said, look, it goes, its trajectory is a superposition of every possible path it can go, round and all over the place, many paths interpretation, and he started to formulate his many path integral. So the idea is that things live in a superposition until they're being observed. I found this extremely weird. It turns out that this kind of phenomena is in pure mathematics. It's within non-commutative, it's within the quaternions. Here we have, what I'm going to do, I'm going to do a rotation in the complex plane. The complex numbers are commutative. If I put the rotation matrix on the left, I get exactly the same as if I put the rotation matrix on the right. I can split the rotation matrix both front and back in two-thirds, and I still get the same answer because everything's commutative. The quaternions are non-commutative. This is a quaternion rotation matrix, four-dimensional rotation. We rotate into a four-dimensional angle, and four-dimensional angle is three real numbers. A two-dimensional angle is one real number, a three-dimensional angle is two real numbers, a 97-dimensional angle is 96 real numbers. This is three real numbers. They fit into the quaternion rotation matrix. I'm going to rotate on the left a particular quaternion vector, which I write as a matrix, and we get this result. That's rotating on the left. We've moved that vector to there. Now I'm going to rotate on the right. Rotate on the right, I've moved that same vector to there, and the two different vectors. The two different vectors because the quaternions are non-commutative. That's what non-commutative means. But what I could do, I could rotate through a third of the angle on one side and two-thirds of the angle on the other side. And in fact, I could do more than that. Because the angle is three numbers, because the quaternion angle is, let me get back up to the rotation matrix. Because the quaternion angle is three numbers, I could put a third of that number on one side, a half of that number on left side, a tenth of that number on left side, 9/10 on the right side, etc. I could split it. I'm still rotating through the same angle, but I'm going to get a different vector as well. What I'm going to get is an infinite set of rotations, all of them different. What I'm going to get is a superposition of eigenrotations. So this idea of superpositions is within non-commutative algebra. This is pure maths. We're not doing physics here. This is pure maths. A non-commutative rotation is a superposition. What did it take to collapse a superposition? Well, and now we're getting to the question of, well, let's talk a little bit about Stern electrons. I'm of the opinion that electron spin is rotation in quaternion space. The electrons, it's not rotation about an axis, because it's a four-dimensional rotation in four-dimensional space. What Stern and Gerlach did, they tried to measure the rotation of the angular momentum of the electron, the intrinsic, well, they didn't try to measure the intrinsic spin because they didn't know about it, but they did measure the intrinsic spin of the electron in a particular direction, shall I say, vertical up and down. And they expected that they'd get all sorts of variation because the actual electrons would be spinning in all sorts of directions. But every time it was either up or down. What they had effectively done, they'd fed three numbers into the quaternion. The three numbers were the vector in four-dimensional space-time that point out the direction. If you feed three numbers into a quaternion rotation matrix, the three numbers being a third on this on the right, a half on the right, a tenth on the right. Yes, your three numbers. Then you collapse your infinite set of your superposition of eigenrotations to just two. The reason it's two is the numbers could be on the right rather than on the left. So that seems to be how you collapse a superposition of eigenrotations. It's done by interaction with four-dimensional space-time. The reason this seems to happen is because the distance function of quaternion space is x squared plus y squared plus is t squared plus x squared plus y squared plus z squared. The distance function of four-dimensional space-time reversed in the sign is minus t squared plus x squared plus y squared plus z squared. The plus x squared plus y squared plus z squared bits are the same. In 3 dimensions, they can interact together. They can fit together. That seems to be the nature of the interaction. When you feed it 3, it's got a choice. It's going to collapse to one of 2 eigen rotations, and it's either up or down. It doesn't collapse half up or half side because it's got no axis of rotation anyway. You send it through a you later select out one of the rotations spinning up. You know the electron's spinning up this way, and you send it through a Stern-Gerlach machine that measures whether it's going to, what its spin is in this way, and you know you're going to get 0 because it's spinning entirely up, but you don't. You get all its spin that way or all its spin that way again. It's forgotten what axis it was spinning on. Well, it was spinning on that axis in 4-dimensional space-time because we're the only space where you actually have an axis for your rotation. In quaternion space, we didn't have an axis, so it's nothing to remember. Right, let's see where we are. I've done that one. So we've done no more than pure maths. We've applied finite groups to the exponential series. We've got all these spaces. Non-commutativities come out because some of the finite groups are non-commutative. And we've got this idea of eigenstates, things existing when they're observed, being in a superposition of eigenstates until they're collapsed by another observation. So these weird aspects of quantum mechanics, the observation seems to be interaction with 4-dimensional space-time. They seem to be within the mathematics. Richard Feynman was of the opinion nobody could ever understand quantum physics. Well, I think we're getting to the point where we can start to understand it. We can see it in the non-commutative algebras. Right, what I did say a while ago is that multiplication is a sequential combination of permutations. Here's an example of a Lie algebra. This is SU3, this is 3 of the 8 matrices in the Lie algebra SU3. They're not permutation matrices. That means you can't multiply them together. That means SU3 is just a palindromic. And the same is true with a lot of mathematics. It's invented by human beings. Sorry, go on, Lou, I know.
Question. But since usually at least, and if we turn something a little bit always, the matrix multiplication can be rewritten as sum of linear combinations of permutation multiplications.
It can.
So that makes that, so from your point of view, doesn't saying that ameliorate the problem? Because if you have a bunch of permutation multiplications and you add them up, then you're really getting matrix multiplication in the way that mathematicians use.
Yes, it does, if you use permutation matrices. But supposing you've got a 4x4 matrix and you've got 16 different numbers in it, that is not a sum of permutations, because your permutations are all ones and zeros. And if you add, you multiply them by no.
So what you end up with is sign permutation matrices, where the signs are. You have a permutation matrix, and then you have some numbers in the places where the permutation ones.
Your numbers have got to be in the right places to suit the permutations. Well, here I've got it. We've got 4 numbers there. They're not permutation because you've got it could have a permutation between 1 there and a 1 there.
Yeah, I think I'll best talk to you about it afterwards.
Okay. Well, if you're very careful about it, and you do have to be a bit careful, the only things you can multiply together are permutation matrices, but it might be that you're actually multiplying together 2 matrices that are permutations in a bigger group than what you thought you were working in. So you have to be a bit careful about that. Here's what kind of thing that we get in particle physics often. That's a permutation. It's I. It's part of the complex numbers. This is not a permutation. We don't have... No, sorry. That is a permutation. It's a permutation in a symmetric group. It doesn't have a representation as 4x4 matrix. That is not the symmetric groups have the representation of in matrix form of the same order as they are. Like S3 has in order 6, a 6 by 6 representation, S4 has 24 by 24 representation. That's a symmetric group section of S4, and it should be in a 24 by 24 matrix, which would be multiplied by a 2 by 2 matrix. Here we have two sets of complex numbers, what we call two spinors. The complex numbers can be written as a quaternion, a left-handed quaternion, not a right-handed quaternion. We'll just put them together like that, and we've got a left-handed quaternion. So what we're doing is we looks like we're multiplying together an element of complex numbers. Well, we could expand that to make it 4 by 4 matrix, which is the equivalent in the quaternions, by 24 by 24, what ought to be a 24 by 24 matrix, by 2 quaternions stuck together in a vector. Mathematically, it's complete nonsense. No matter how you try to adjust it, it don't work. And I think that's about with it. With possible renormalization of the loops in virtual particles. When we do this, we discover that there's a left-handed electron and a right-handed electron. It seems that what we did last year predicts the virtual particles as well as the actual particles. The virtual particles come out directly out of the groups. The superpositions of those virtual particles form the actual particles. When we come to do QED, and we come across problems with loops, calculating in loops, because we get infinities. And basically we ignore the infinities and call it renormalization. I don't know, but I speculate if instead of using the electron as a virtual particle, we use the left-handed electron and the right-handed electron, and a left-handed positron and a right-handed positron, that the left-handedness and the right-handedness must cancel and we solve the renormalization problems. I don't know, I haven't done it. A little bit about general relativity. General relativity is a mathematical system within four-dimensional space-time. Four-dimensional space-time is not an algebraic structure. So you can't really multiply within it, but you can multiply within the 6 algebraic structures whose superposition is four-dimensional space-time. So if you want to do gravity theory, you do the calculation every one of the 6 spaces that form four-dimensional space-time, and you take the superposition. That's one way of doing it. Einstein comes up with the idea that space is curved. The complex plane cannot be curved. You try to curve the complex plane or put a little pimple into it, a little bit hump into it, the whole algebra collapses completely. All these algebraic spaces are bang flat. So we've got a four-dimensional space-time that Einstein says is curved, formed of 6 bang flat spaces. Well, it can't be curved. You can't curve these algebraic spaces. But what might happen is they might misalign. The curvature in general relativity is portrayed within the metric. It's given in the metric, which is a 4 by 4 matrix that's effectively got 10 numbers in it. Some of the numbers are duplicated to the top and bottom to make it look pretty. Those 10 numbers are what the metric does. It compares a standard coordinate system, 4-dimensional coordinate system, 4 axes, with another 4-dimensional coordinate system that's slightly off. The 4 numbers down the center, the leading diagonal of the metric, measure the relative scaling of the axes, of the 4 axes. The other 6 numbers measure the angle between the axes, and they're measured as in the products in the metric. We'll take 3 space, we'll take the 3 that form right-handed space, 4-dimensional space-times. We've got 3 spaces to compare then. One of them we set as the reference space. How do we know that those spaces align perfectly with each other? Well, we don't know whether they do or not. But if they are out of alignment, it would take 10 numbers to measure how much they are out of alignment. Scales on the axes and the angles between the axes. It's a metric. That gives you how much out of alignment they are. The third one, also you get a metric for. The superposition of those 2 metrics is a metric. And so you will get exactly the same results if you attribute gravity to non-alignment of the spaces as you would if you attributed it to curvature. My personal view is that's not correct, but it would work. And I can't say it's wrong, it might be right. My personal view is that we've got to develop the equations of motion for gravity within the 6 spaces, and that we simply use those. I'll talk a little bit about, well, dark matter, which that seems to be gravitational field energy, the gravitomagnetic field energy, which doesn't cancel. Neutrino mass. About 2 million years ago, a supernova went off in the Magellanic Cloud, came to Earth, it hit Earth in 1987 in the Neutrino Observatory in Antarctica, I think. And they got 19 neutrinos that all came at once, bang. By this you know that neutrinos travel at the speed of light, because if they'd have travelled at less than the speed of light, they wouldn't have travelled at exactly the same speed, and they would have been spread out as they came, rather than bang all coming at once. They also came exactly 4 hours before the light got here, which is what the calculations and understanding of supernova says they should do. So we have a fact, neutrinos travel at the speed of light through a vacuum. Therefore they're massless. The mathematics we did last year showed that the neutrino field was a quaternion with 0 real part, i.e. 0 mass. But the quaternion interacting with its conjugate gets a non-zero real part, mass squared. What you need for neutrinos to oscillate is you need mass squared. There's a little bit of bad notation in physics where they've just put the mass instead of the mass squared. The physicists go around saying neutrinos must have mass to oscillate. They mustn't. They must have mass squared. They're massless when they go through the vacuum. They get mass when they interact. So the solution to the neutrino mass problem is quite obvious. When a neutrino is formed in the centre of the sun, it interacts on the way out from the sun, and it gets mass squared. The mass shows the interaction, and so it oscillates. It comes across the vacuum of space, massless at the speed of light, gets to the Earth, interacts with the Earth's atmosphere, and oscillates a little bit more. So the solution is that neutrinos are massless as they go through the vacuum, and that they gain mass squared by interacting within a medium. We know that light travels slower than the speed of light through water, through a medium. And so the implication is that light is massless when it travels through a vacuum and travels at the speed of light, but because it travels less than the speed of light through a medium, it actually becomes massive. So one prediction of the theory that is possibly experimentally testable is that light gets mass when it's moving through water or some other medium that slows it down. So, there we are. That's the end of it. Questions and comments?
Any questions? I'll do that if you got any questions.
Questions? It's either very good or very bad.
I'm not very good at all this, but something pops up in my mind.
Recording stopped.
If you have the idea about moving something in space, you know, with a big mirror,
Yeah.
and you throw light at it to move it out in space.
Yeah.
How does it move if there's no mass in light in space? It just pops up in my mind.
You've lost me completely.
It's like if you have a laser.
Yeah.
With light, that's light, right? Going out in space. And if light is massless when it travels in vacuum in space,
Yeah.
then if you have the idea about placing a satellite in space with a big mirror on it, and then you believe that putting a laser on that one, you can move that satellite in space.
Yeah.
That's the things.
Yeah, it is observed that if you shine light on something,
Yeah.
it moves it, it bangs into it, it's got momentum.
Yeah.
And one of the big questions of physics is how can something that's got no mass have momentum? And the answer, standard answer is just accept it.
Okay. Yeah,
but that's not a good enough answer, is it? That's not a good enough. What supposing that it hits the mirror and it interacts with the mirror and it gets mass while it's interacting because it's travelling slower through the glass.
That makes sense. Yeah.
That would give it momentum, wouldn't it?
Yeah.
Now, I don't know whether that's right or not. It's certainly not the standard answer. The standard answer is don't ask such awkward questions. But of course, that's what we should be doing, is asking such awkward questions.
Yeah.
But yeah, I mean, light, when it hits something, it does have momentum. And you can actually say, I saw this in a Batman comic, years ago, when Batman showed Commissioner Gordon that he could rotate a little black painted propeller by shining light on it. Yeah. I was 7-year-old when I learned about that. But yeah, that's what I think the answer might be.
Any more questions? What about the people on Zoom? Have you got any questions? Go ahead, Nicola.
It's not, because it's like most of it is totally over my head, right? But so I come in at certain places where things sort of jump out, obviously connected with other things I've been thinking about, and there are a number of things I was very interested in, but one of them was to do with the exponential series, that this is very fundamental in some way that I didn't quite understand, but I'm very interested in because exponential as numbers come very late on the scene, right? So in fact, they're ones that I've kind of wondered about more. So, like pi, where you can
I think Euler discovered exponential series about 1790 or something.
That's still quite late into it.
Yeah. I'm not going to show the dates.
That's not the first discovery.
Is it not? No.
It existed in the 70s. A century before.
Okay.
Yeah, the exponential series contains all types of numbers, complex numbers, quaternions, everything that's in mathematics, every algebraic field. It also contains every type of rotation, because when you differentiate the exponential series, you split it in half, you differentiate it, you get the second half. Like cosine differentiated gives you sine. The cosine is a measure along the horizontal axis, the sine is a measure of the vertical axis. So what that's saying is that the measure on the vertical axis is equal to the rate of change with respect to the angle. Is the rate of change of the actual measure on the horizontal axis. As you rotate it, this is cosine. This is the differential of cosine with respect to the angle, and that's what rotation is. It's this differentiating to cycles. If you take those three-dimensional trigonometric functions, you differentiate it 3 times, you get the 3 cycle. They are partial because there's 2 variables involved, it's partial differentiated, but they repeat over and over again. Same with the quaternion functions, they're harder to differentiate because they're not commutative. And all the 97-dimensional commutative rotations are just differentiated in 97 cycles. And that's where you get the rotation from. And so the whole of space, and indeed our 4-dimensional space-time, because it's a superposition of these spaces that's in the exponential series, is within the exponential series. And all the gauge groups that give us the electron and everything else, the gravity, quarks, they are also in the exponential series. So within the exponential series, I've got all of this, and even me.
Right. I think we ought to finish now, Dennis. Well, thanks very much for your talk. And we'll have a 10-minute pause, I think, for the next.